We have seen black holes. We have measured their weight. We have felt their gravity bend space-time like silk pulled tight. But the singularity, the supposedly infinite heart of a black hole, does it truly exist? Or is it merely the stutter of mathematics when human understanding reaches its limit? This video promises to unravel a profound misunderstanding that has lingered for decades. Leave a comment below. Do you trust what can be observed, or what no one has ever seen? And to understand why this question matters, we must begin with what cannot be denied. Black holes, what we know for certain is real. What does it mean to find something that never shines, never glows, never reflects a single photon back toward your eyes, and yet can rearrange the heavens as casually as a hand stirs smoke? Black holes entered human knowledge not as monsters in a telescope, but as fingerprints on the world. We did not meet them face to face at first. We met them the way you meet a powerful stranger in a dark room. By the pressure in the air, by the sudden hush in the conversation, by the way everyone else leans without understanding why toward one invisible point. In the beginning, the evidence was humble and beautifully ordinary. Stars behaving oddly, gas moving too fast, light flaring where no star should be able to power it. And then, slowly, the pattern tightened into something unmistakable. A black hole is not a metaphor. It is a physical object, an extreme region of space-time whose gravity is so intense that the usual rules of escape, the usual hopes of maybe, simply fail. If that sounds like certainty, it is because science earns its confidence the hard way, not through one dramatic observation, but through many different kinds of observations agreeing with each other like independent witnesses. One line of evidence comes from motion. In astronomy, motion is confession. A star can hide its secrets, but it cannot hide how it moves. Near the center of our own Milky Way, astronomers watched stars swing around an unseen focus, tracing looping, elegant paths year after year. Those orbits were not gentle. They were fast, tight, and mercilessly controlled by something massive, packed into a region too small to be a cluster of ordinary stars. The stars were like leaves caught in an invisible whirlpool. No matter how skeptical you begin, there is a moment when the dance becomes too precise to explain away. Gravity is writing a signature in the sky, and the signature says, "There is a vast mass here," and it is compact beyond common sense. Another line of evidence comes from light itself, not light emitted by the black hole, but light tortured by its presence. A black hole is not a lantern. It is a sculptor of the surrounding world. Gas falling toward it heats up, accelerates, and glows in X-rays and radio waves, forming a swirling, luminous disk like a bright river circling a drain. Sometimes that river launches jets, vast beams of particles and radiation that punch through interstellar space for thousands of light years. We see these jets not because the hole shines, but because the environment around it screams under gravity's grip. It is a cosmic lesson in indirect seeing. The black hole is the absence at the center, the still point around which everything else is forced to reveal itself. To see a black hole, then, is to see what it does. It is like knowing there is a wind on your skin when the air itself is invisible, because the trees bow, the water roughens, and dust lifts in spirals from the ground. Or think of standing outside a house at night, hearing a deep bass note through the wall. You cannot see the speaker, you cannot see the music, but the vibration arrives in your bones and removes doubt. In the same way, we infer black holes through the motion of nearby stars, the heat of infalling gas, the bending of light, and the ripples in space-time itself. And those ripples' gravitational waves may be the most haunting evidence of all. When two black holes spiral together and merge, they do not merely collide, They ring the universe like a bell. Instruments on Earth, unimaginably delicate, have detected those space-time tremors. It is hard to sit with that fact and remain unchanged. Two objects, utterly dark, utterly unreachable, merging in a distant galaxy, and the echo arrives here, passing through our planet, through our bodies, through the quiet air of an ordinary day. In that moment, black holes stop being ideas and become events. The cosmos has mass, it has motion, and space-time itself can carry news. This is why John Wheeler's famous line, "Black holes have no hair," still matters, even beyond its technical meaning. It suggests something almost poetic, that black holes are defined not by a messy biography, but by a stark simplicity, as if nature, at the edge of extremes, chooses to speak in a minimalist language. And then there is Stephen Hawking's disarming reminder: black holes are not as black as they are painted. In one sentence, he opens a door. The objects we feared as perfect darkness are, in a deeper sense, participants in the universe's story, capable of radiating, changing, evolving, and challenging our assumptions. Now, what makes a black hole different from every other celestial body is not simply that it is heavy, or dense, or dramatic. It is that it creates a boundary with a peculiar kind of finality, the event horizon. Cross that horizon, and the paths that light can take, the very geometry of escape tilts inward. A planet can be left. A star can be escaped. Even a neutron star, fierce as it is, remains a place from which, in principle, a message can return. But a black hole introduces a one-way region in the fabric of reality. It is not merely an object in space, it is a reshaping of what possible means. And yet, to keep this grounded in something you can picture, consider two simple examples. First, imagine an ice skater spinning with arms extended, then pulling them in. The spin speeds up not by magic, but by conservation of angular momentum, a quiet rule of nature. Around black holes, gas does something similar. As it spirals inward, it speeds up, heats up, and brightens. The black hole is the reason the motion becomes extreme, but the glow you see is the skater's speeding spin translated into cosmic terms. Second, imagine a school of fish suddenly turning in perfect synchrony because a predator moves beneath the surface. You might not see the predator at first, but the pattern in the water reveals it. In the galaxy's center, the school is a swarm of stars, and the predator is gravity concentrated into a compact, unseen mass. You cannot deny the predator once you've watched the turn. What's remarkable is how these clues, stellar orbits, glowing accretion disks, jets, gravitational waves, interlock. They do not depend on one instrument, one wavelength, or one style of measurement. They are different languages saying the same thing. That is why the discovery of black holes is not a fragile claim. It is a converging conclusion. But there is also a deeper invitation here, one that fits the quiet, meditative mood of looking into space. Black holes teach us that reality is not obligated to be intuitive. They ask us to let go of the childish demand that we must see directly in order to believe. In daily life, we trust invisible things all the time: gravity itself, radio waves, the magnetic field that guides a compass, the thoughts behind someone's eyes. The universe is simply asking for the same maturity, trust built on pattern, on prediction, on the disciplined humility of evidence. And once you accept that black holes are real in this grounded, observational sense, another question begins to glow in the dark, like a distant ember. If we can be so certain about the horizon, about the mass, about the spin, about the way nearby matter behaves, then what exactly is that thing people call a singularity? Is it a physical feature of nature, or a sign that our equations, brilliant as they are, become incomplete when pushed beyond their rightful domain? If black holes are real, could the singularity be something else entirely? An artifact, a placeholder, a warning label printed by mathematics when it reaches the edge of what it can describe? Hold that thought, because the next step is where the story turns from discovery to mystery, from what we can measure to what we can only approach with careful imagination. We begin, as we must, with the part we know is solid under our feet, the black hole itself, and the evidence that makes it undeniable before we dare to step closer to the boundary where certainty thins into questions. What if the most important part of a black hole isn't the center at all, but a silent boundary where the universe draws a line and says, no further messages will return? When most people imagine a black hole, they imagine a cosmic drain, a bottomless throat, a dark heart where everything ends. But the true drama doesn't begin at the imagined core. It begins at the event horizon, a surface that isn't really a surface, a border that isn't really a wall, and yet a boundary so absolute that it defines what a black hole is more cleanly than any picture we could draw of its interior. The event horizon matters because it is not a guess about what happens in the unreachable depths. It is a statement about what can happen in our world, in the part of reality where cause and effect still talk to each other. You can think of it as the universe's last shoreline. Beyond it, not even light can send a postcard home. Not because light gets tired, or because darkness swallows it like an animal, but because space-time itself is tilted so steeply that every possible future path points inward. There is something almost meditative about that idea, as if nature has built a place where the future has only one direction. John Wheeler captured the strange simplicity of this realm with a line that still echoes through physics. A black hole has no hair. In other words, once you cross that threshold, the outside world no longer cares about the intricate story of what fell in. The horizon becomes a kind of cosmic editor, reducing complexity to a few clean facts. So what happens to light as it approaches this boundary? Imagine a traveler walking toward a doorway that is not locked, not blocked, but simply leads out of the shared world. From far away, you would see their steps slow, their movements stretch, their signals arrive more and more delayed, like a voice becoming drawn out across a widening canyon. This isn't because they are struggling. It's because time itself is behaving differently near such extreme curvature. Light climbing out of that gravitational well loses energy. Its wavelength lengthens, it reddens, it dims. Approaching the horizon, the light is red-shifted more and more until, for distant observers, it fades toward invisibility. The horizon is not a velvet curtain that absorbs light on contact. It is the place where the geometry of space-time makes escape routes disappear. Here's a way to picture it without equations. Think of a fast river flowing toward a waterfall. A fish upstream can swim against the current, cross the river, explore, but as the fish nears the brink, the current strengthens. There is a point where the water moves downstream faster than the fish can possibly swim upstream. Past that point, the fish can still move, still live, still perceive, but it can no longer return to the upstream world. That point of no return is not a physical barrier in the water. It is a boundary defined by speed and flow. In a black hole, the flow is the structure of space-time, and the horizon is where that flow inward outruns even light. A second example is quieter, almost domestic. Imagine standing in thick fog with a friend holding a flashlight. At first, you see the beam clearly. As the fog thickens, the light looks dimmer, more diffuse, harder to recognize as a message. If the fog becomes dense enough, the light doesn't stop existing, it simply stops reaching you in a meaningful way. Near a black hole, the fog is not mist but gravity's effect on time and energy. The light still travels locally at light speed, but what reaches a distant observer becomes increasingly stretched, delayed, and drained of energy. The message isn't destroyed, it is exiled from the shared timeline. And this is where something beautiful happens, something surprisingly reassuring. The event horizon is not where physics breaks, it is one of the places where physics shines brightest. General relativity, our best theory of gravity, works extremely well in describing what happens at and just outside the horizon, as long as we are not demanding an impossible view from inside. The equations remain calm and coherent there. The horizon can be enormous and gentle, especially for supermassive black holes. If you were falling into one, the local experience at the horizon might not feel like a dramatic impact at all. The real violence, the tidal tearing, depends on the black hole's size and how rapidly space-time changes across your body. For a stellar mass black hole, the gradients can be merciless. For a supermassive one, the gradients at the horizon can be comparatively mild. The horizon is not a singular spike of infinite gravity. It is a boundary of information. Stephen Hawking once put it with his signature mix of clarity and wonder: "Black holes ain't as black as they are painted." That sentence carries an important lesson. The horizon is not just a mouth that eats. It is also a stage where quantum ideas and gravitational ideas whisper to each other. Hawking's work suggested that black holes can emit radiation, which means the horizon is not merely an endpoint, it is a kind of thermodynamic object with temperature and entropy. Even if the deep interior remains mysterious, the horizon behaves like something we can describe, test, and measure, a threshold with physical properties, rather than a purely fictional boundary. But if the horizon is so important, how do we measure a black hole's mass and size when the thing itself is dark? This is where science becomes almost poetic in its patience. We do not weigh a black hole by touching it. We weigh it the way we weigh a hidden mountain, by watching how rivers bend around it. We watch the dance of stars and gas in its gravitational grip. In the center of our own galaxy, astronomers tracked stars moving in tight, fast orbits around an unseen object. Those orbits revealed a mass millions of times greater than the Sun, packed into a region too small to be anything else we know. The black hole announced itself not with light, but with authority. Gravity, here, is a signature that cannot easily be forged. We also measure black holes by listening. When black holes collide, they shake space-time itself, sending gravitational waves outward like ripples across a cosmic pond. The waveform carries information about the masses and spins of the objects involved, and even about the ring-down, the final settling into a new black hole. It is the sound of geometry relaxing into a stable shape. From these signals, we can infer the size of the event horizon indirectly, because in general relativity the horizon scale is tied to mass. Larger mass, larger horizon. The horizon becomes a measurable idea, not a mere metaphor. And sometimes, remarkably, we can almost see the horizon's silhouette. The Event Horizon Telescope did not photograph a black hole directly, because a black hole does not emit light. Instead, it imaged the glow of hot materials swirling around it, and the dark shadow cast by the gravitational bending and capture of light. That shadow's size matches what we expect from a black hole of a given mass. It is like seeing a campfire's light wrap around a standing figure in the dark. You don't see the figure's face, but you know it is there because the light tells you what it cannot pass through. All of this is why the event horizon is more important than the imagined center for most of what we can honestly claim. The horizon is where observation, prediction, and measurement meet. The center, by contrast, is where our theories are forced to extrapolate into conditions we cannot yet test, and where the word singularity may be less a description of reality than a warning label on our mathematics. The horizon is the part of a black hole that belongs to the universe we can question. It is the boundary where the cosmos speaks clearly, even as it withholds its deepest secrets. And perhaps this is the most human lesson hidden inside the darkest objects we know. We stand outside the horizon the way we stand at the edge of our own understanding, not defeated, not denied, but invited into deeper precision. The event horizon is not merely a place where things vanish. It is a place where meaning sharpens. It asks us to separate what we can measure from what we only imagine, to respect the difference between mystery and myth, to be humble without being helpless. So now, with the shoreline mapped and the boundary made real, we can take the next step. Because once we understand why the horizon is stable, measurable, and physically meaningful, the question that follows becomes unavoidable, almost intimate in its urgency. If physics remains strong at the edge, then where exactly does it fail? And why did we ever call that failure a thing? In the next part, we move from what the universe allows us to observe to what our equations claim must exist deep inside. And we ask the quiet, unsettling question at the center of this entire story. If the black hole is real, is the singularity anything more than a placeholder for what we have not yet learned? Have you ever noticed how the most terrifying ideas in physics often arrive quietly, not with a bang, but with a single symbol on a page that refuses to behave, a number that grows without mercy until it becomes infinite? The singularity enters our story exactly like that, not as a photographed object, not as a measured signal, but as a destination inside certain solutions of Einstein's equations where the mathematics pushes itself into a corner and starts shouting, "I can't go any further." In the language of general relativity, gravity is not a force in the old, mechanical sense. It is geometry. It is the shape of space and time themselves. John Wheeler captured the heart of it in one of the most quoted lines in modern physics. Space-time tells matter how to move. Matter tells space-time how to curve. When we take that relationship seriously, we discover something both beautiful and unsettling. If you compress enough mass into a small enough region, the curvature can become so extreme that paths through space-time tip inward. Like rainwater finding the lowest drain, a black hole forms, complete with an event horizon, a boundary from which light cannot return. This part is not mythology. It is observed. It is tested. It is, in the most sober sense, real. But the singularity is different. The singularity appears when we keep following the equations deeper, past the event horizon, into a region we cannot observe directly. In the simplest black hole solution, the curvature grows as you approach the center, and certain quantities surge toward infinity. Density, in the naive picture, becomes infinite. Volume shrinks toward zero. The equations suggest a point where the normal rules of space and time no longer make sense. And so the word enters, singularity, a place where the theory blows up. The atmosphere of that word is almost religious, as if we have found the altar of the universe. Yet in physics, an infinity is often not a revelation, it is a warning flare. Why does infinite density and zero volume create such a deep physical contradiction? Because infinities do not fit inside the operational meaning of science. Physics is built on measurement, on comparisons, on units that retain their meaning. An infinite density is not just a very large number, it is the collapse of the question itself. It is like asking for the exact color of a shadow in total darkness. When volume goes to zero while mass remains, our ordinary concepts break. Temperature, pressure, energy density, curvature, even the notion of here and there begin to lose coherence. The singularity, as a literal object, would require nature to store an unbounded amount of something in a place with no size. That is not merely extreme, it is undefined. So what is a singularity really? One honest answer is that it is a signpost that says, this description of the world has reached the edge of its jurisdiction. General relativity is a magnificent theory, but it is classical, smooth, continuous. It treats space-time like a perfectly woven fabric. Quantum physics, however, whispers that the fabric may not be perfectly smooth at the smallest scales. If space-time has a grain, a trembling, a minimum unit of meaningful structure, then the infinite point may be a mirage produced by using the wrong language in the wrong place. It is not that general relativity is wrong in the way a simple mistake is wrong. It is that it may be incomplete in regimes where quantum effects can no longer be ignored. There is a quiet, educational humility hidden in this. When mathematics returns infinity, it does not always mean the universe contains infinity. Sometimes it means our model does. Imagine you are sailing at night with an old map, and the map ends at the edge of the paper with the words, "Here be dragons." The dragons are not necessarily real. The paper is. The limit is. The warning is. The singularity may be our dragons. Not because the universe is fantastical, but because our map runs out. Here is one way to feel that in your bones. Think of a magnifying glass held over a printed photograph. From far away, the image looks smooth, continuous, almost alive. As you zoom in, the face becomes a landscape of dots. If you insist the image must remain smooth at every scale, you will start making strange predictions. You might claim that within one dot, there are smaller dots, and within those dots, smaller dots still, until you reach a point of infinite detail. But the infinity is not in the photograph. It is in the assumption that the photograph is infinitely smooth. Your model is refusing to admit the grain. In much the same way, the singularity can arise from extending a smooth, classical picture into a region where smoothness may no longer be a valid idea. A second example is closer to everyday intuition. Picture a river rushing toward a waterfall in thick fog. You can measure the current upstream. You can see the water accelerate. You can predict that it will continue faster and faster until it plunges. But in the fog, you cannot see the lip of the falls. Your equations may tell you the speed grows without bound as you approach some imagined point, because you're extending the river model beyond the place where it applies. The infinity is not a physical speed, it is your inability to describe what happens at the edge with the tools you are using. The singularity sits behind the horizon like the hidden waterfall, not necessarily as an object of infinite density, but as the place where our description stops being trustworthy. Stephen Hawking, who spent a lifetime wrestling with the paradoxes of black holes, once said, "Black holes ain't as black as they are painted." It's a line that feels almost playful, yet it opens a serious door. If black holes can radiate, if they can slowly evaporate through quantum effects, then the interior story cannot be told purely with classical geometry forever. Quantum physics seeps in, like dawn light entering a room you believed was sealed. And once quantum physics enters, the singularity becomes less like a destination and more like a placeholder, a blank space in the narrative where a deeper theory must speak. This is where the conversation turns from fear to fascination. The singularity is not merely a scary center. It is a question mark placed by the universe at the exact point where our two greatest theories stop agreeing. General relativity wants a smooth geometry that can curve without limit. Quantum mechanics refuses infinities in that way and hints that reality at small scales is jittery, quantized, relational. If both are true in their domains, then a black hole's heart becomes the ultimate classroom, the place where nature forces our thinking to mature. And that brings us back to the first question. Where does the singularity come from? It comes from our insistence on pushing a classical equation into a regime where it may not apply, and then treating the resulting infinity as a physical thing rather than a mathematical distress signal. It is born at the intersection of brilliant insight and human limitation. It is what happens when a tool that works beautifully for stars, galaxies, and expanding space is asked to describe the last whisper of distance and time. If you listen closely, you can hear something almost meditative in this. The universe does not owe us an easy picture. It offers clues. It offers patterns. It offers a horizon, both literal and intellectual. The event horizon is real, but it is also symbolic, a reminder that knowledge has boundaries, and that beyond those boundaries, certainty becomes a softer, more careful word. The singularity may not be a physical thing you could point to, but it is absolutely real as a problem, a pressure point, a lesson written in the grammar of the cosmos. So when mathematics gives infinity, what is it truly saying? Often it is saying, you have reached the edge of the map, not the edge of reality, the edge of your current language. The black hole is real. The evidence is there in orbiting stars, glowing accretion disks, and ripples in space-time itself. But the singularity, as a literal point of infinite density, may be less like a hidden object and more like a mirror held up to our theories, showing us exactly where they stop being complete. And maybe that is the deeper beauty. In the silence behind the horizon, the universe is not mocking us. It is inviting us. It is saying, gently but firmly, you have come far, but not far enough. The question is not whether the singularity is there like a rock at the bottom of a well. The question is what new way of thinking will appear when we finally learn how to describe what happens when space-time itself is pushed to its most intimate limit. What if the most terrifying place in the universe is not where space collapses, but where our understanding does? We like to imagine the singularity as a physical point, a real location buried inside a black hole like a seed inside a fruit. A tiny dot where everything falls, everything ends, everything becomes infinitely dense. It is a vivid picture, and it feels satisfying, because the human mind craves an ending it can point to. But the moment we try to describe that dot with the tools of modern physics, something quietly breaks. Not the black hole, not reality itself. Our equations. Outside a black hole, and even near its event horizon, general relativity performs like a beautifully tuned instrument. It predicts the bending of light, the slow stretching of time, the way matter spirals into a glowing disk and screams in X-rays before it disappears. It is the reason we can look at the motions of stars around Sagittarius A times and say, with sober confidence, there is something massive and compact there. It is the reason we can listen to gravitational waves and recognize the final seconds of two black holes merging, a cosmic bell struck across the darkness. In those realms, relativity feels almost spiritual in its precision, a geometry so elegant it borders on poetry. And yet the same equations, pushed further inward, begin to produce a strange kind of nonsense, the mathematical equivalent of a compass spinning wildly. Curvature becomes infinite, density becomes infinite. Time, as the equations describe it, runs into a wall. When the math outputs infinite, it isn't always announcing a real infinity in nature. Often, it is confessing something else. It is telling you, softly but firmly, you have asked this tool to do a job it was never designed to do. That is why our current laws stop applying at the so-called singularity, because singularities, in physics, are frequently the scar tissue of an incomplete theory. A signpost that says, new physics needed beyond this point, not an altar that says, here lies the final truth. One way to feel this, without drowning in equations, is to remember how science has met infinities before. Consider a map of Earth drawn on a flat sheet of paper. It works beautifully in many places. You can navigate cities, measure distances, plan a journey, but push that flat map toward the poles, and the distortions swell until the geometry looks absurd. Greenland inflates into a continent-sized illusion. Lines that should behave begin to misbehave. The map has not revealed a monstrous polar reality. It has revealed the limits of the projection. The singularity may be our pole, our distortion, the place where the projection of relativity onto the deepest interior becomes too stretched to remain truthful. Or picture a microphone recording a gentle song. For most notes, the sound is faithful, but crank the volume higher and higher until the waveform clips, flattening into harsh noise. Did the singer become infinite? No. The instrument saturated. The recording system reached the edge of what it could represent. In the same way, the infinite density at a singularity can be read as the clipping of our mathematical microphone, not the literal scream of reality becoming infinite. The deeper reason this happens is the collision between two masterpieces that were never fully reconciled. General relativity is a theory of the large, planets, stars, galaxies, the shape of space-time itself. Quantum mechanics is a theory of the small, atoms, particles, uncertainty, the grainy probabilities that underlie matter. Each is astonishingly successful in its own domain. Each is confirmed by experiments with almost humiliating precision. And yet, when you try to make them occupy the same room inside a black hole, they begin to argue. Relativity says gravity is geometry, smooth and continuous, like an endless fabric. Quantum mechanics says nature has a restless, jittering undercurrent, a fundamental uncertainty that refuses to be ironed flat. Relativity tends to treat space-time as a calm stage on which matter performs. Quantum mechanics insists the stage itself should quiver, fluctuate, and perhaps be made of discrete pieces. Near a singularity, the densities and energies implied by relativity become so extreme that quantum effects can no longer be ignored. The small becomes unavoidable. The probabilities begin to matter. And our two best languages for describing the universe start translating the same reality into incompatible stories. This is why many physicists suspect that the singularity is not a place, but a boundary of description, a horizon, not for light, but for knowledge. There is a famous line attributed to Albert Einstein, "God does not play dice." It captures his discomfort with the probabilistic heart of quantum theory, his sense that reality should be definite beneath the apparent randomness. But then Richard Feynman, with his blunt honesty, offered the counterpoint that still humbles every student of physics. I think I can safely say that nobody understands quantum mechanics. Between those two sentences is the tension we carry into every black hole. One voice longing for a clean, deterministic truth, another reminding us that the universe may not be obligated to be intuitively understood. So when relativity predicts a singularity, One interpretation is not that space-time literally tears into an impossible point, but that relativity, acting alone, is being asked to describe a regime where it cannot stand without quantum support. It is like trying to describe the behavior of water using only the rules of ice. You can get far. You can build structures and make predictions. But at the moment of melting, your rules stop being rules, not because nature is broken, but because your description is incomplete. And this leads to the most important shift in perspective. Perhaps the singularity is where physics collapses, not where space collapses. That sentence sounds simple, but it is a profound reorientation of the mind. It means that our diagrams of black holes as funnels ending in a pinpoint may be less like photographs and more like myths, useful metaphors that become dangerous when taken literally. It means that what lies inside may not be a point at all, but a region governed by principles we have not yet learned to speak. It means the black hole is not just an object in space, but a challenge to the way we do knowledge. And if that is true, then the singularity is not the final answer. It is the invitation. What might replace it? Some ideas suggest a quantum core, where space-time resists being squeezed beyond a certain scale, not unlike how matter resists being compressed once quantum pressures awaken. Others imagine that what falls in is not destroyed at a point, but transformed, smeared, or reorganized in ways that preserve information in a form we cannot yet decode. Some theories hint that space-time itself is not continuous all the way down, that at the deepest level it becomes granular, and the notion of a smooth point loses meaning the way a perfect circle loses meaning when drawn on a pixelated screen. None of this requires sensationalism. It requires humility. Because the existence of a singularity in our equations does not certify the existence of a singularity in nature. It may instead certify the honesty of science, the willingness of our models to raise a hand and say, "Not here, not yet." And that might be the most educational, almost meditative lesson hidden inside the black hole. There are places in the cosmos where our confidence dissolves, where our neat categories loosen, where certainty becomes a quieter, more cautious thing. Not because reality is unknowable, but because knowing is a journey, not a trophy. So yes, black holes are real. Their shadows have been captured. Their mergers have been heard. Their gravity has been measured with the patience of decades. But the singularity is different. The singularity is a word we use to mark the edge of our current story. And as we step toward the next part of this journey, hold on to that distinction like a lantern in the dark. The black hole is an object. The singularity may be a question. The black hole is something the universe does. The singularity may be something our mathematics does when it runs out of breath. And now, with that question glowing in the mind, we can begin where certainty still exists, where evidence still speaks clearly, where the cosmos leaves fingerprints we can actually read. The black hole. What we know for certain is real. What if the most dramatic part of the black hole story, the singularity, is not a destination at all, but a warning sign, a red light on the dashboard of our equations asking us to slow down? Because black holes themselves are not in doubt anymore. We can watch stars orbit something unseen at the center of our galaxy. We can map the glow of hot gas spiraling toward an invisible boundary. We can listen to the faint, exquisite ringing of space-time when two massive objects collide and merge. The black hole is real in the way mountains are real, in the way storms are real. Yet the singularity, the point of infinite density where the laws of physics supposedly shatter, is a different kind of claim. It is not something we have observed. It is something that appears when we push our current mathematics past the region where it was ever meant to be trusted. Albert Einstein once wrote, "The most beautiful thing we can experience is the mysterious, and black holes, more than any other object in nature, are the purest form of mystery that still belongs to science. They are not fantasy. They are not mythology. They are the universe insisting, calmly and relentlessly, that our picture of reality is incomplete. And perhaps the singularity is the clearest example of that incompleteness. In many ways, it behaves like a word we wrote into the story because we did not yet know how to write the next paragraph. To see why, imagine a map drawn by an early explorer. The coastline is accurate for hundreds of miles, the rivers and hills are sketched with care, and then, at the very edge of the parchment, where the ink runs out and knowledge ends, a warning appears. Here be dragons. The singularity can feel like that. Not a place we have visited, but a label placed at the boundary where our theories stop giving sensible answers. General relativity, Einstein's masterpiece, describes gravity not as a force but as geometry, as the bending of space-time itself. It works beautifully, almost eerily, for planets, stars, galaxies, and the slow dance of cosmic structure. But when gravity becomes too intense, when matter collapses beyond a certain limit, the equations begin to predict infinities. Density goes to infinity. Curvature goes to infinity. Time and space, as we understand them, break apart. And in physics, infinity is often a confession. It is the theory admitting it has been asked a question outside its jurisdiction. This is where the if becomes powerful. If there is no singularity, then what is inside a black hole? Not as a cheap twist, not as a gimmick, but as a serious scientific possibility. One path forward is the idea of a quantum core, a region where space-time is no longer smooth, no longer a continuous fabric, but something granular, something stitched from discrete threads of quantum geometry. The phrase quantum core might sound abstract, but the intuition is simple. We have learned, again and again, that the world changes its behavior when you push it into extreme regimes. The classical rules that guide everyday objects do not apply cleanly to atoms. The rules that guide atoms do not apply cleanly to nuclei. Why should space-time itself remain obedient to classical geometry when compressed beyond all precedent? Here is one way to picture it. Take a soft ball of cotton and squeeze it. At first, it yields easily. Keep squeezing, and it resists more strongly. You can compress it, but the resistance grows. Now imagine doing the same with matter under gravity, except the squeezing is not done by your hands, but by the weight of the collapsing star itself. And the resistance is not just from the material, but from the quantum principles that govern what can be packed into the same place at the same time. Many physicists suspect that, at some point, the collapse should encounter a new kind of pressure, not the pressure of gas or radiation, but the pressure of quantum space-time, as if the fabric of reality has a stiffness we only notice when we try to fold it too sharply. This is where ideas like the Planck star enter the conversation. The concept, associated with approaches like loop quantum gravity, suggests that collapse does not proceed to an actual point of infinite density. Instead, it reaches a maximum compression around the Planck scale, an unimaginably tiny regime where quantum gravitational effects become dominant. At that point, the interior could bounce, not like a rubber ball in ordinary space, but like a universe-scale recoil within the black hole's hidden depths. From the outside, the black hole could still look stable for immense spans of time because gravitational time dilation stretches internal processes. A bounce that occurs quickly inside might take eons to appear as anything noticeable from far away. It is a haunting possibility. The black hole, outwardly quiet and eternal, could inwardly be a slow-motion metamorphosis. Another family of ideas comes from string theory, where the singularity might be replaced by something called a fuzzball, a tangled configuration of strings and brains that fills the region we once imagined as empty interior. In this view, the black hole is not a simple void with a point at the center. It is more like an object with structure spread throughout, a dense quantum state that mimics a horizon from a distance, but does not require an infinitely compressed point. The details are technical, but the message is almost poetic. The interior is not a blank abyss. It is information-rich. It is complexity. It is texture hidden behind an outwardly smooth silhouette. And then there are proposals like gravastars, where the collapse triggers a kind of phase transition in space-time itself, forming a shell-like structure with an exotic interior that avoids the singularity. This is not unlike the way water changes identity when it freezes. The molecules do not vanish into infinity. They reorganize. They become a new phase of the same substance. If space-time can undergo a phase change under extreme curvature, then perhaps the center of a black hole is not a place where reality ends, but a place where reality changes state. That brings us to the question of how much matter can be compressed before new physics appears. In everyday life, compression feels straightforward, but nature has layers. There is a point where atoms lose their individuality and electrons become a sea. There is a point where nuclei are forced into close contact and matter becomes neutron-rich, as in neutron stars. There may be a deeper point still, where the distinction between matter and the geometry it inhabits becomes blurred. In these regimes, it may not even make sense to ask where matter ends and space-time begins. John Archibald Wheeler captured the spirit of this relationship in a line that has become almost a mantra in modern physics. Space-time tells matter how to move. Matter tells space-time how to curve. Under ordinary conditions, that exchange is gentle. Inside a collapsing star, it becomes a roaring feedback loop. Matter curves space-time. Curved space-time guides matter inward, and the cycle intensifies until either a singularity forms or something new intervenes. Here is a second example to make the intuition tangible. Picture a crowded highway at rush hour. Cars flow smoothly until density rises. Then you hit a threshold and the entire behavior of the system changes. Suddenly, there are stop-and-go waves that move backward through the traffic even though every driver wants to move forward. Nothing infinite happened. No mystical point appeared. The system simply crossed into a new regime where the rules of motion look different. In a similar way, a gravitational collapse might reach a threshold where the smooth, classical description breaks down, and a new collective behavior of space-time emerges. The singularity, in that analogy, would be like concluding that traffic density must become infinite because your simple flow equation cannot describe a jam. The better conclusion is that your equation has met the limits of its assumptions. So, could space-time transition rather than collapse without bound? It is not only possible, it is arguably the most reasonable expectation if we believe that quantum theory is fundamental. A smooth continuum all the way down to zero size is a very classical idea. Quantum physics teaches us that nature often refuses such extremes. Energies become quantized. Fields fluctuate. Vacuum is not empty. Even nothing has structure. If space-time is subject to quantum principles, then the idea of compressing it into a mathematical point of infinite curvature may be as physically unrealistic as compressing an ocean into a single droplet without changing its nature. None of this diminishes the black hole. If anything, it makes the black hole more profound. The horizon remains a real boundary in the sense that it marks a limit to what can communicate outward. The gravitational redshift remains real. The tidal forces remain real. The ring-down signals from mergers remain real. The black hole is still the universe's most extreme laboratory. But the singularity may be less like a throne at the center of darkness and more like a placeholder, a symbol of ignorance dressed up as a destination. And perhaps that is the most educational value of this question. Not that we get to declare a final answer, but that we learn how science behaves at the edge. We learn the difference between observation and extrapolation. We learn that equations are powerful, but they are also stories we tell about the world, and every story has a domain where it speaks clearly and a domain where it begins to stutter. If the singularity is not real, then the inside of a black hole is not a dead end. It is a frontier. It is a hidden workshop where space-time and matter renegotiate their contract. And the next time we hear the chirp of a gravitational wave, or see the luminous ring around a shadow, we might remember that we are not merely witnessing a cosmic monster. We are watching the universe place a question mark at the center of our certainty, quietly inviting us to keep going, deeper, with humility. So when you imagine the interior of a black hole tonight, don't picture a mythical point where reality collapses into nothingness. Picture a threshold, a transformation, a secret architecture under pressure, and ask yourself, softly but seriously, if the singularity is only a sign that our map ends here, what new landscape is waiting beyond the last line of ink? What if the darkest object in the cosmos is not a destroyer at all, but a messenger we have not learned to listen to yet? A black hole feels like the universe's ultimate act of silence. Matter falls in, light cannot return, and every familiar signal is swallowed without a trace. It is natural, almost human, to assume the same fate for information. If a book is thrown into a fire, the words seem to vanish. If a star collapses into a black hole, do the details of everything it consumed vanish as well, not into smoke, but into something even more absolute than smoke, into a place where gone becomes a permanent law? This question has haunted physics for decades because it is not only about black holes, it is about whether reality keeps receipts. It is about whether the universe is forgetful, or whether it remembers in a language too subtle for our instruments, too quiet for our intuition. Stephen Hawking once quipped, "Black holes ain't as black as they are painted," and in that playful sentence lies a revolution. The old picture of a black hole was a perfect prison. Nothing escapes. Therefore, everything that falls in is erased from the outside world forever. But Hawking's work suggested something startling, a kind of faint breathing from the edge of the abyss. In the quantum view, empty space is never truly empty. It trembles with fleeting particles, appearing and disappearing like brief thoughts in the mind. Near the event horizon, this restlessness can be amplified, producing what we now call Hawking radiation, a slow leak of energy from the black hole itself. Over unimaginably long times, this leak implies an even more unsettling possibility. Black holes might evaporate, not with a dramatic explosion, but with a patient, cosmic exhale until the giant that once devoured stars is reduced to nothing we can point to. And that is where the question sharpens into a blade. If a black hole evaporates, what happens to everything that went in? If the hole eventually disappears, does the universe simply delete the information it consumed, like a cosmic shredder that leaves no scraps behind? Physics, as we understand it, is reluctant to accept that. In the quantum world, information is not a decorative detail, it is the skeleton of predictability. If information can be destroyed, then the rules that connect yesterday to tomorrow begin to loosen. Cause and effect become less than a promise. The universe becomes a place where the story can change without warning, and science itself becomes a fragile habit rather than a reliable method. To feel why this matters, imagine a simple example. Picture two identical envelopes sealed shut, one containing a love letter, the other containing a grocery list. From the outside, they look the same. Now imagine dropping both envelopes into a black hole. If information is destroyed, then the universe does not just burn the paper. It erases the difference between love and routine, between confession and inventory, between two distinct histories. The world becomes less specific. Reality becomes less faithful to detail. Yet our experience of physics, from the smallest particle experiments to the grand architecture of stars, suggests that nature is obsessed with bookkeeping. Even when things transform, the deep accounting tends to balance. Hawking radiation, however, seems to complicate that faith. The radiation looks thermal, like the random heat glow from a warm object. Thermal radiation does not care about the fine details of what created it. A cup of tea cooling in a room releases heat, but the heat does not carry a map of the tea leaves. So if Hawking radiation is truly random, it seems to offer an escape route for energy but not for the information itself. That is the heart of the information paradox. Gravity says nothing gets out. Quantum theory says information cannot be destroyed. Hawking's result says black holes can evaporate in a way that appears to wash away the details. The paradox is not a small disagreement. It is a crack that runs through the foundation, where two of our greatest theories meet and refuse to blend. Now, bring in the singularity, that supposed point of infinite density at the center. Many physicists suspect that the singularity is not a physical thing at all, but a sign that our current equations are being pushed beyond their rightful domain. In older ages, maps contained blank edges labeled with monsters, not because monsters were real, but because knowledge ran out. A singularity may be one of those blank edges. If that is true, then information might never be truly trapped in an infinite point. It might be stored, transformed, or encoded in ways that do not require infinities. And suddenly the question becomes less about a mythical center and more about the horizon, the boundary where the black hole meets the rest of the universe. Here, the conversation becomes strangely philosophical, almost meditative. A horizon is not a wall you can touch. It is a relationship. It is the point beyond which signals cannot reach you. It is defined by what can be known from where you stand. If information is preserved, perhaps it is preserved at this boundary, like a memory held on the surface of a deep lake. You cannot see into the water, but the surface still ripples with the truth of what moves below. This is why the idea of black hole entropy and surface area became so important. It whispered that black holes behave less like bottomless pits and more like objects with a finite capacity to store information, and that the storage is strangely tied to the horizon itself, not the volume inside. John Wheeler captured a similar intuition with 3 simple words: it from bit, matter from information, reality from a kind of cosmic code. If Wheeler's aphorism is even partly true, then the information paradox is not a side problem. It is a direct challenge to what the universe is made of at its deepest level. Perhaps the black hole is not a trash can for information, but a pressure chamber that forces information to change form, like coal becoming diamond. Not lost, but reorganized under extremes. A second example can help make this less abstract. Imagine a vast library where every book is shredded, then burned, and the smoke is released into the sky. To a casual observer, the stories are gone. Yet in principle, the smoke contains the atoms that were once ink and paper, and those atoms carry the history of their arrangement, even if it is scrambled beyond practical recovery. If you could measure every particle, every motion, every interaction with perfect precision, you could, in theory, reconstruct what was destroyed. The difference between lost and scrambled is the difference between chaos and annihilation. Many modern approaches to the black hole problem lean toward the idea that information is scrambled to a degree that feels like loss, while remaining, in principle, preserved. This is where the idea, if there is no singularity, becomes more than a technical preference. Without a singularity, the interior might not be an endpoint where physics breaks and information is crushed into impossibility. It could be a region governed by quantum gravity effects we are only beginning to imagine. A place where space-time itself behaves like a medium with microscopic structure. In such a view, information might be protected not by magic, but by deeper laws. It might be encoded in correlations, subtle relationships between particles, woven into the outgoing Hawking radiation in patterns so delicate that we mistake them for randomness until we know how to read the weave. And if that is true, it changes how we understand the universe in a quiet but profound way. It suggests that reality is not a stage where objects appear and disappear, but a tapestry where nothing truly vanishes, only changes its form and its accessibility. The universe may have its own kind of compassion for detail. The falling of a photon into darkness may not be a funeral. It may be a translation. The black hole, then, is less like a cosmic grave and more like a cosmic engine, compressing history into new languages, forcing us to expand our notion of what exists means. Of course, we should be honest about the limits. We do not yet have a complete theory that merges quantum mechanics and gravity. We do not yet fully understand how information would be encoded and released in every scenario. But what is educational here is not certainty. It is the shape of the question and how it disciplines the mind. The black hole information problem teaches us that nature is not obligated to match our intuition. It teaches us that a boundary can be more important than an interior, that the act of observing is tied to what can be communicated, that the universe might conserve not only energy and momentum, but the very distinctness of events. So when we ask, does information really disappear into a black hole? We are asking something tender and human beneath the physics. Are we living in a reality that forgets, or a reality that remembers? When Hawking radiation whispers from the horizon, is it a random hiss or a coded confession? And if the singularity is not real, if it is only a warning sign on the map, then perhaps the true heart of the black hole is not a point of infinite destruction, but a frontier of hidden order. If you had to choose right now, what feels more like the universe you live in? A universe that erases or a universe that transforms? Leave your thought in the comments, not as a verdict, but as a question you are willing to carry. And as we move forward, let's begin where certainty still holds, with the one thing our instruments and equations agree on, the doorway that is undeniably real, the black hole itself, and the measurable, haunting boundary we call its horizon. What if the darkest object in the universe is not a place where knowledge dies, but a place where knowledge finally admits its limits? We call it a black hole, and that name already feels like a confession. Not because it is empty, but because it is so full of gravity that light itself cannot climb out. We have watched stars whip around an invisible mass with the obedience of iron filings around a magnet. We have listened to space-time ring like a bell after distant collisions, as if the universe were briefly struck and allowed to sing. We have even traced the silhouette, that haunted shadow, against a glowing disk of superheated matter. In that sense, the black hole is not a metaphor. It is an observed fact. And yet, just when we feel most certain, the old question returns like a tide in the dark. Are we observing the black hole, or are we touching the edge of what the human mind can truly hold? Because the moment we say singularity, the story changes. The word is elegant, almost poetic, like a single point of absolute truth. But in physics, elegance can be a warning label. A singularity is not something we have seen. It is what appears when our equations keep marching forward into a domain where they were never promised to survive. It is the place where numbers explode to infinity, where density becomes infinite, where curvature becomes infinite, where language itself begins to stutter. And when mathematics starts shouting infinite, it may not be describing a real object. It may be telling us, calmly and mercilessly, that we have reached the end of a map, not the end of the world. Albert Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." That line carries a quiet double meaning. Yes, the cosmos yields to reason in astonishing ways, but it also implies something else, that comprehensibility is a strange gift, and gifts have boundaries. The black hole feels like the boundary made visible. It is the point where the universe becomes so extreme that our normal categories, space, time, inside, outside, begin to blur. We can still do excellent physics at the edge. We can calculate orbits, energy flows, lensing, tidal forces. We can build instruments that gather faint whispers from far away and turn them into human understanding. But when we push inward, deeper than any signal can return, the imagination longs to keep going, and the equations follow, until suddenly they do not. This is where the singularity becomes a kind of philosophical mirror. It asks whether our theories are the universe, or only our best translation of it. General relativity is magnificent. It tells a coherent story about gravity as geometry, a story that has survived every observational test we've thrown at it in the regimes we can check. Yet relativity is not the final language of reality, because at small enough scales, the quantum world does not politely step aside. The quantum insists that nature is grainy, uncertain, probabilistic, stitched with fluctuations. We have two great books on the same shelf, both written in the handwriting of the cosmos. And at the black hole's core, the pages overlap and the ink runs. John Wheeler, one of the architects of modern gravitational physics, offered a line that feels almost like folklore. Black holes have no hair. In other words, once a black hole forms, it forgets the detailed identity of what fell in, and presents itself to the outside world with only a few simple traits. That idea is powerful because it suggests the universe is capable of radical simplification, turning complexity into purity. But it also provokes unease. If the black hole forgets, where does the information go? If the story is erased, what does that say about the world's deepest bookkeeping? The singularity has often been treated as the ultimate vault where the ledger is locked away. And that is exactly why the concept may not survive the next chapter of science. Nature is subtle, but it is not usually sloppy. Infinity feels less like an answer and more like a placeholder. Think of it like this. Imagine you are using an old nautical chart, drawn by brilliant hands with limited tools. It is accurate along the coasts and the trade routes. It shows the currents, the safe harbors, the cliffs. But at the bottom edge of the parchment, where the known world fades, the mapmaker sketches a sea serpent and writes a warning. The serpent is not necessarily real. It is the artist's way of saying, beyond this line, the certainty ends. a singularity may be our sea serpent. Not a lie, not a joke, but a symbol marking the boundary where a framework stops being trustworthy. Or consider a second example, closer to everyday life. You place a microphone too close to a speaker, and suddenly the system erupts into feedback, a shriek that overwhelms everything. The scream is not a hidden voice from another room. It is the sound of the apparatus, amplifying its own limitations until it collapses into noise. When equations produce infinities, we should at least entertain the possibility that we are hearing feedback, not revelation. The singularity might be the point where our mathematical microphone is too close to the cosmic speaker. None of this diminishes the black hole. If anything, it makes the black hole more extraordinary, because now the black hole becomes not merely a thing in space, but a test of the human project of knowing. It forces us to ask what it means to understand something we cannot directly enter, cannot sample, cannot return from. We are used to science as a lantern that pushes back darkness. But black holes remind us that sometimes the lantern shines brightly only to reveal the shape of the darkness itself, crisp and undeniable. This is why the question about ether is so haunting. There was a time when ether felt necessary, a substance imagined to carry light the way air carries sound. It was a reasonable idea, even a beautiful one, until experiments refused to cooperate. Eventually, physics did not merely adjust ether, it released it. Not because the universe had changed, but because our picture of it had matured. The history of science is filled with such quiet goodbyes. And perhaps the singularity will join that list, not as a defeat, but as a graduation. We might look back one day and say, we used that word as a bridge, until we could build a better one. So what could replace it? Here the conversation becomes tentative, as it should. Some possibilities suggest that at extreme densities, space-time does not continue smoothly into a point, but undergoes a kind of quantum transformation. Maybe there is a smallest meaningful scale, a limit beneath which location stops being a sensible concept. Maybe the core is not a point, but a region governed by new rules, where geometry becomes foamy, where time behaves differently, where the idea of inside is not what we think. These are not claims. They are signposts pointing toward work not yet finished. But they share a common spirit. They treat infinity not as a destination, but as a warning that we have walked beyond the safe edge of our model. And that brings us back to the last question, the one that lingers like a slow note in a cathedral. What is the black hole hiding about the deep nature of reality? Perhaps it is hiding nothing at all, and the hiding is in us, in our expectation that every mystery must yield to a clear picture. Or perhaps it is hiding a unity we have not yet learned to see, a way that quantum and gravity are not enemies but two faces of one deeper structure. The black hole could be telling us that reality is not built only from things, but from relationships, from information, from horizons, from the strange fact that what you can know depends on where you stand. In the end, the most educational value of this topic is not the thrill of the unknown. It is the discipline of humility. The black hole is real. The shadow is real. The orbiting stars are real. The waves in space-time are real. But the singularity may be something else. Not a thing in the universe, but a crack in our description of it, inviting repair. And if that is true, then black holes are not just cosmic monsters. They are teachers. So here is the question I want to leave gently in your hands, like a stone warmed by the sun, then cooled under night air. If the universe allows us to see the outline of a black hole, but refuses to show us its center, is it because the center is physically unreachable, or because the very idea of a center is an old habit of thought that the cosmos is asking us to outgrow. As we come to the end of this journey, one truth stands quietly above the rest. Black holes are not symbols or speculations anymore. They are measured, observed, and woven into the structure of modern astronomy. Yet the idea of the singularity reminds us that certainty has limits. When our equations point toward infinity, they may not be revealing the universe's deepest secret, but exposing the edge of our current understanding. The lesson here is not that science has failed, but that it is still growing. What black holes ultimately teach us is humility. They show us that reality can be profoundly real without being fully accessible. We can trace the motion of stars, detect gravitational waves, and map the shadows cast by immense gravity, while still accepting that some regions of nature remain beyond direct reach. The singularity, then, may not be a place where physics ends, but a signpost telling us that a deeper framework is still waiting to be discovered. Just as past generations once relied on ideas later set aside, our own concepts may one day be refined, replaced, or quietly retired. There is also a more human lesson woven into this story. Knowledge does not advance by clinging to certainty, but by learning how to live with unanswered questions. Black holes remind us that not knowing is not ignorance, but an invitation. An invitation to listen more carefully, to imagine more gently, and to remain open to the possibility that the universe is richer than any single theory can contain. Thank you for taking this time to explore these ideas with me. Your curiosity, your reflections, and your willingness to question are what keep this conversation alive. If this story sparked a thought or a quiet sense of wonder, I invite you to share your perspective in the comments. And above all, thank you for watching, for listening, and for continuing to look into the darkness, not with fear, but with curiosity.